uh, interacts in the environment sequentially, making decisions and learns to take optimal decisions. So the RL objective is to maximize the discounted cumulative reward, which is defined by R, where gamma is the discount factor. So here, like say an episode, there's an entire episode which consists of T time steps. So the agent interacts over there, taking T different actions at every time step and receiving some rewards. And then GT is the entire sum, basically the sum of the entire sum of all the rewards that received throughout the entire episode. The two key definitions consist of the value function that is only state dependent and the action value function, which is dependent both on the state and the action. The value function is basically the expected reward that we receive given that currently we are in state S. And the action value function is the expected return that we can get given that we start in state S and take an action A. These are really important definitions which we'll be using throughout the presentation. So our problem is formulated using a Markov decision process. So what is Markov property? Markov property is that given the present, uh, given the current state, it is okay to not know the past state to decide on the action to be taken. So current state is enough for making the decisions for the future. So here MDP is defined by the tuple given as, which consists of state S, which represents a set of all the states in the MDP. Then it consists of U, which represents the set of all the actions or control inputs available for the agent, which it can take in the environment. P is the state transition probability matrix, which defines that from if we take some action U in some state S, what is the probability of transitioning to some state S dash. R represents the reward that will be received given that we are in state S and take some action U. And gamma is the discount factor, which determines the trade-off between the immediate and future rewards. Now, not all the environments that we want to work with are fully observable. So there's this concept of partial observability, where there's some observation probability matrix defined by this capital O, which determines the observation that we see, the partial observation that we see, given that the environment state is S and we take some action U, we land up in a state S dash, where the agent is only able to observe the partial environment, partial state of S dash, that is small o. Now let us look into policy gradients. So in policy gradient, we directly try to learn the optimal policy that is given some state S, what is the optimal action that we should be taking. And we can parameterize the policy as a neural network with parameters theta, and it can be computed as the given formulation here. So here we can see that the log probabilities of the action are scaled by the return that we receive throughout the episode. So this is a basic formulation of the policy gradient algorithm. A more advanced version, which is more reliable, is called as the actor critic algorithm. So in actor critic algorithm, we make use of both the actor, that is the policy, and the critic, which is the value function. So here, instead of using the episodic return for scaling the action probabilities, what we do is we use the advantage function. That is, what is the advantage of taking a specific action in a given state over the other actions? And the advantage function is defined as the expected return given that we start in state S and take an action U minus the expected return from that state. So this basically gives out the advantage of taking action U in that given state. Next, let us look into multi-agent reinforcement learning. Multi-agent reinforcement learning can be classified in two ways based on the types of agents that are in the environment or based on the reward that the agents receive in the environment. So based on the type of agents, the environments can be classified as homogeneous agent environments or heterogeneous agent environments. In homogeneous agent environment, all the agents in the environment have the exact same set of state space and the action space. Whereas in heterogeneous agent environment, the state space and the action spaces can be different for different agents. And based on the reward types, and a multi-agent environment can be either cooperative environment where all the agents work towards a common goal, or a competitive environment where there might be two teams or n number of teams which compete against each other, or probably just two agents competing against each other. Then there are more complex environments which have mixed goals, that a few goals are competitive, whereas few other goals are cooperative. So a cooperative multi-agent RL problem can be solved, formulated as a DEC POMDP, that is decentralized POMDP. The state-of-the-art approaches use centralized training, decentralized execution approach. Some of the most common state-of-the-art algorithms in off-policy MARL are VDN or QMX, and in on-policy algorithms are IPPO or MAPPO. A DEC POMDP, that is decentralized POMDP formulation, is given by this tuple where S is the environment state. And as in this scenario, as the environment is cooperative, we are only considering the homogeneous agents environments. So all the so the state space for all the agents is common, that is S. The action space for all the agents is U, and say some agent I selects an action UI. So the joint action for all the agents combined is this bold U. And the local observation for all the agents will be Z. So this Z is a partial observation, which is sampled based on the function. Say tau, that is an action observation history of some specific agent I, then the decentralized policy can be defined as pi I of the probability of action U for agent I, given the trajectory that that agent has observed. And the objective here is to maximize the common reward that all the agents receive. So here you can see that the action taken is, so the reward is dependent on the action of the entire team. Now let us look into PPO and MAPPO. So PPO is a variant of actor-critic algorithm, which uses a clipped objective, which helps in better convergence overall. So PPO is one of the state of the art in current single agent algorithms. And MAPPO is a multi-agent extension of PPO, where each agent learns its own policy, but the critic is a centralized critic and has privileged access to all the information of all the agents' states. The centralized critic learns the joint value function of the cooperative environment. Some of the common challenges in reinforcement learning include exploration of the environment, sparse rewards, partial observability, and reproducibility. Some of the challenges specific to multi-agent RL are exponential growth and joint action space with increase in number of agents. Another common challenge is the non-stationarity introduced due to learning co-players. And there's really slow experience collection because we have to do computations for all of the agents in the environment for taking one step in the environment. Now, this is a bit separate concept called a spectral normalization, which we'll be using in our work. So spectral normalization is basically normalizing the weight matrix of the network by its largest spectral value, which constrains the specific layer to be one Lipschitz continuous. So spectral normalization was introduced for stabilizing discriminated learning in GANs. In context of reinforcement learning, spectral normalization has been used in various other works, which on algorithms of policy algorithms like DQN or DDPG. In our work, we'll be applying spectral normalization and multi-agent on policy algorithm. So now let us look into the first part of the work, that is effects of spectral normalization in multi-agent RL. So what is the objective here? Our objective here was to see how learning happens in sparse rewards on policy cooperative multi-agent environments. So our contributions mainly include that we introduce a sparse reward configuration for the StarCraft multi-agent challenge map and show that it is difficult to learn for the standard on-policy algorithms. We propose to regularize the critic with spectral normalization and show that it learns better policies even under sparse rewards. And finally, we analyze the effects of applying spectral normalization and show that it helps one in stabilizing the critic gradients and has an optimization effect of scaling the gradients of the entire critic by the product of the largest spectral value. This is more of a theoretical result, which we'll be skipping in this presentation. So we mainly do our experiments on two environments. One is robotic warehouse, which is a sparse reward environment where there are multiple agents and the agents need to collect the demanded inventory from the shelves and deliver it. And the agents will be rewarded only for successfully delivering the inventory. And then there's a StarCraft multi-agent challenge where there'll be, this is a standard multi-agent game where there are two teams, and with one team wins when all the agents in the other teams are killed. So as mentioned, we introduce a sparse reward configuration for the SMAC setting. So in the standard SMAC setting, each agents in the ally team are rewarded for the reduction in health, either in their own team or in the enemy's team. What we do is we discard this dense reward and we only reward the agents for either killing the enemy team or having some death in their own team. So that introduces a lot of sparsity throughout the learning, because it's not that one shot is able to kill an enemy in the opponent team. So for our work, we use MAPPO, and our network architecture, it's an actor critic algorithm. So the actor consists of a 3-layer recurrent network where the middle layer is the LSTM layer. And the critic network is a 3-layer feed-forward network. So what are the experiments that we do? So we mainly apply spectral normalization on the critic part, and we have 3 different variants. That is applying spectral normalization on the entire critic network, applying spectral normalization only on the second layer or the middle layer of the critic, and applying spectral normalization only on the final layer. And then we use standard MAPPO as a baseline. So here are the results on robotic warehouse environment, where we see that both MAPPO as well as this mid-SN MAPPO are performing pretty good. The final performance is almost the same. However, we can see in one of these maps that applying spectral normalization does lead to a little bit faster convergence and a bit stable learning. So this environment didn't give us much insight into the effects. So then we started looking into the StarCraft multi-agent setting. And here, I think the results are way more evident. That when in a sparse reward setting, we can see that the red line is the standard MAPPO baseline, which doesn't learn at all in this specific map. And whereas we can see that all the spectral normalized critic networks are able to learn at least something. But we can see that the best performing agent, which is more stable overall, is when applying spectral normalization in the last layer. Now, when we look at, so in this first environment, that it is like 3S5Z versus 3S6Z. There are 8 agents in the ally team, whereas 9 agents in the enemy team. So we wanted to test our effectiveness in a more, say, in an environment where there were a lot more agents. So we tested it on 27 and 30M, where there are 27 members in the ally team, whereas 30 members in the enemy team. And even in this scenario, where the overall action space and the number of agents increased drastically, we can see that the last SNMAPP is performing really good. And all the other variants are performing better than the baseline variant. But the interesting results come when we look at the corridor environment. In corridor, we see that the last SN MAPPO and full SN MAPPO both are like not able to learn at all almost, whereas the standard MAPPO does do something, and the mid SN MAPPO is able to converge faster, but it doesn't like do really good. So after, moreover, like the first 2 environments where we saw good performance are kind of like an open world maps where there's a really wide open ground and both the teams come and like fight against each other. Whereas corridor is a unique map where there are like 2 really small corridors through which the opponent team and the ally teams are separated. And so sometimes when during the battle, if they get stuck in the narrow alley, then it'll be, and if they're surrounded by the opponent team, then it'll be easier for their team to lose and the surrounding team to win. So here the strategies are not that smooth. So when we look into analyzing the gradient norms of the networks, so what exactly is causing this better learning? So we can see that in the corridor environment, the gradient norm the gradient norm is really high for the standard MAPPO, whereas the gradients for the spectral normalized version critics are relatively better. It is important to notice the log scale on the y-axis. But when we look at the 27M, 30M environment where the gradient norms are not that different. So there is some effect based on the gradient norm, but not necessarily always. So it's not that the stabilization of gradients is always helping. So that there might be some other effect that could be causing this better learning. Moreover, we saw that in corridor environment, that the mid SNMA VBO and the standard baseline version are performing almost the final performance is almost the same. So when we look at the number of enemies killed, we can see that our version is always able to kill more enemies, even though the win rates are almost the same. So yeah, overall it is doing a little better, but it is not that evident just by looking at the win rates. So what are the drawbacks and benefits of the system? The main things that we realize by analyzing all of these and doing these experiments is that applying spectral normalization does help in stabilizing the critic because it constrains the network layer to be one which is constant, and that's why it helps in stabilizing the gradients. Another thing that is a theoretical work that is that the optimization effects that scales the gradient by the inverse of the maximum spectral value. And the third point is that there's better learning of smooth value functions by applying spectral normalization. But an RL environment might not have a smooth reward function throughout the entire environment. So the drawbacks is that the spectral normalization can only help us to an extent under the conditions that the agent is able to reach some rewarding states. If the agent is not able to see any rewards at all, so if we change the settings to if we change the smack setting to instead of rewarding for deaths of the enemy and ally team members, if we just change it to just the final reward where at the end of the episode we give only win or lose rewards, in that scenario we observe that there's no learning at all. And the other one is that when we apply the spectral normalization to the final critic layer, SN only helps when the value function to be learned is really smooth. So that is what we saw in the case of corridor, where we saw that the map is a bit complicated and it requires more elaborate strategies to win. So the value functions will not be really smooth over there, and hence we didn't see much learning if we apply it to the final layer. So that concludes our first work, and probably this work can be extended such that while our work has successfully addressed moderately sparse rewards, like it'll be interesting to investigate if the effects on extremely sparse reward scenarios, because it very likely doesn't work over there. Our research was primarily focused on cooperative multi-agent setting in this work. So it would be beneficial to extend this work to investigate in competitive games or maybe mix some games to understand how it will be effective in the other general multi-agent scenarios. It'll also be interesting to investigate other regularization methods. So we only investigated spectral normalization. So something like instant normalization or something like that might also help equally good. So yeah, that would also be another interesting direction to explore. Now we look into the second part of the work, that is MARL-JAX, that is a multi-agent framework that we developed for social generalization. So our objective here was to develop an open source scalable MARL framework for social generalization research. Our contributions include a JAX-based framework for training and evaluating social generalization of the trained MARL policies. It is loaded with features like multi-GPU training and distributed experience collection when the environments are CPU-based, which enables large-scale experimentation and really long training. We also provide two strong baseline implementations. One is multi-agent actor critic, which is Impala-based architecture, and an algorithm called as options as responses, which is specifically designed for social generalization. And we evaluate our implementation on two commonly used benchmarks, Melting Pot, which is from DeepMind, and Overcooked, which is from UC Berkeley. So yeah, we support two environments, Melting Pot and Overcooked. And yeah, let us look into that. So Melting Pot is an environment suite which is specifically designed for evaluating social generalization of the agents. So Melting Pot defines some keywords called as substrate, background population, and scenario. Substrate is basically a standard multi-agent environment with n players. The environment can either be cooperative, competitive, or general sum game. The background population is basically pre-trained policies which specialize in some specific skills and which are provided by the environment suite itself. And then there is scenario. So scenario is basically a multi-agent environment with n minus k players, where k is the population size of the background population. So here, during the training time, we have access only to the substrate, whereas the background population and scenarios are used to evaluate the social generalization of the trained agents. So what exactly we mean by social generalization? So in the previous work in cooperative setting, we saw that all the, like say there's an environment of seven agents. Then once we do the training of all of these seven agents, during the evaluation time, the distribution of the co-players in the environment will always stay the same. But in case of social generalization, we would like to evaluate what if the distribution of the co-players changes. What if we sample only same player again and again, that is sampling only the single policy winner, or maybe we do uniform random sampling from these policies of co-players. Or like we looked into the scenario that say three players are from the background population and other four agents are from one of these trained policies. So this will help us evaluate the generalization capabilities of the trained agents. So as this is mostly a software work, to enable like really scalable training, we basically provide with three or four different training pipelines. One is the standard sequential training, where we use the policy which interacts with the environment and collects the experience. Then that collected experience is used by the learner to learn the parameters. But this is a really sequential process and it can be really slow. And given that we are collecting experience from only one environment, neither the CPU nor the GPU resources are utilized optimally. Then to like at least start using the CPU more optimally, we introduced a synchronized training paradigm where we create multiple instances across different processes for the environments, and then we collect the experience from all of these environments in parallel. But here the point is that each interaction with the environment happens synchronously. So we take a set of actions, all the actions are provided to all of these environments, then we wait for the uh, processes in the environment to finish and return a state, and then all of these states are collected in the policy. Given that policy is a neural network, we can do batch inference to collect the experience. So here, this increases the speed a little bit, but not to a satisfactory level. And the GPU is always sitting idle during the experience collection process. So how can we optimize this even further? So that's why we introduced an asynchronous training pipeline. So this kind of training pipeline has been used in single agent training, and we scale it up for a multi-agent training setting. So here what we do is there are n number of processes spawned up where the experience collection happens asynchronously. Each process has its own copy of the policy network weights, and the inference part is done totally on the CPU. And all of these processes keep on collecting experience, and there's one common replay buffer server which collects the experience from all of these processes, and there's a learner process which is separately running continuously with samples from the replay buffer and keeps on training the network parameters. So here we can see that a learner process is continuously utilizing the GPU, whereas all of these processes are continuously utilizing the CPU. So here, like, we obtain a really optimal resource utilization. But as we know that the policy is a neural network policy, so inference on CPU might become a bit of a bottleneck. So for that, we introduced a common inference server-based architecture where, so in each process, we can spawn up multiple environments and multiple such processes like that. And what they do is in all of those processes, each environment takes an action in the environment, receives a state. That state is asynchronously sent to some inference server, which, and this inference server process always runs on the GPU. So now the overall speed might increase. So yeah, this is architecture which helps into better utilization of GPU resources and overall increases the speed compared to the previous architecture. So these are the four architectures that we implement. And we test our implemented algorithms, that is options as responses and the standard critic baseline on melting pots running with scissors. So running with scissors is a rock, paper, scissors game basically in a matrix. So given that we are in a matrix world, there are resources of rocks, papers, and scissors, and there are two agents spawned. Each of these agents can roam around the environment and collect the resources that they prefer. And then at the end, they play against each other based on the set of resources they have. So it has a standard matrix payout. You can refer to the original paper for that. And so here what happens is if the opponent is playing rock, it will be good for the focal agent to play paper. If the opponent is playing scissor, then the main player has to play rock. So the players have to adapt their strategies based on what the opponent plays. So here we can see that the standard actor critic algorithm is not able to learn anything and stays pretty close to zero reward. Whereas options responses, which is specifically designed to adapt to opponent strategies, even during the inference time, we can see that it is able to receive positive rewards. And there are like 5 different scenarios available from the melting pot scenario, melting pot suit, and we can see that the options as responses is able to receive positive reward in all of these scenarios, whereas Impala is doing good in 2, doing bad in the other 2, and almost 0 in the other scenarios. So we can see that our implementations are accurate and we are able to achieve decent results. We also evaluated on overcooked scrammed room. So yeah, this is the basic training plot. Yeah, I think this summarizes our work. So to extend this work, like our code base serves a strong foundation for future research for social generalization and generalization to novel co-players in multi-agent learning. As we focus mostly on speeding up the experience collection part, given that the environments run on CPU. So it would be really interesting to have, say, GPU-based implementations of environment, which would even speed up the environment interaction part. And JAX has the benefit of JIT compilation, so we could compile the entire end-to-end training pipeline. So yeah, that would be an interesting future work. So in conclusion, like in the first part, we look into the issue of learning a reliable critic and multi-agent sparse reward scenarios. And in the second part, we introduced MARL JAX, that's a powerful software package for multi-agent learning, which focuses on training and evaluating social generalization of the events of the agents. So these are the 2 resulting publications from our work. Yeah, so I guess, thank you. So if anyone has any questions. Yeah, like if you have any questions, you will have to talk because I can't see the chat. Yeah, I believe if there are no more questions, then we can end the presentation here.
Hello?
Yes, sir.
Yeah, thanks for the talk. Yeah. So it seems there are no more questions here. If anyone has
Yeah.
question, then yeah, you can ask.